love this section. I even like the next section better. I love these sections. Integration by substitution. Here we go. In exercises 17 through 24, use the indicated substitution to evaluate the integral. Confirm your answer by differentiation. We won't do that last part. But the reason I skip all the way to 18 is because like 1 through 17, you really already know how to do. And you'll see when you get to the homework. Number 18. We need, here's the theme. You ready for the theme? We need to find a function and its derivative. A function and its derivative. That's what you need. A function and its derivative. All right, that's going to be really loud on the film. We're going to let u, this is section 7.2, right? Let u equal 2x squared. Because that's the function. Now, we need a function and its derivative, but all we really need is a function and a multiple of its derivative. That's what we need. So then du is equal to 4x dx. Now we don't have a 4x dx. We have an x dx. Now this is multiplication, so the order doesn't really matter. I have the integral of, oh no, not yet. I'm not ready for that yet. I don't have 4x dx. I have x dx. So we have 1/4 du equals x dx. And that's why all we need is a multiple of it, because we can just get whatever we don't need, whatever we don't have, we just get it to the other side. X dx is replaced by 1/4 du. So 1/4 du. And I try to pull all constants out of integrals. Get them out of there. Well, now instead of cosine of 2x squared, we have cosine of u, and we know how to integrate cosine of u. It happens to be sine of u. We have 1/4 sine of u plus c. So we have 1/4 sine of 2x squared plus c. And imagine what you do if you took the derivative. It says, show that it works by differentiation. Show that it works by taking the derivative. All right, you don't have to do this, but we'll do it. The derivative of sine is cosine of 2x squared times 4x. Well, that 1/4 cancels out the 4, and you get the x cosine of 2x squared. Yeah, it works, right? All right, now the next one, we're going to let u equal as much as possible, but not too much. So as much as possible would be 7x minus 2. Now I can't have 7x minus 2 to the third, because then you have the chain rule, and the derivative is way too much. So du is equal to 7 dx. Well, I don't have a 7 dx. I got a 28 dx. So 4 du is equal to 28 dx. That's why it's okay to have a multiple of the derivative, because they'll just multiply. Or, if I have to, I can do some division like we did on the one before. 28 dx is going to be replaced. 28 dx is replaced by 4 du. And then we have not 7x minus 2 to the third, but we have u to the third, which is 4 times, I add 1 to the power, u to the fourth, but then times 1/4. Well, those are going to cancel each other out. I got u to the fourth plus c, and so I eventually have 7x minus 2 to the fourth plus c. Imagine if you took the derivative. You'd have 4 times 7x minus 2 to the third, but then times the derivative of the inside, which would be 7. And you get 28 out on the outside. Questions on that? Let's keep rolling then, so we can get to the homework. All right, here we go. U equals as much as possible, but not too much, so that the derivative is really complicated with the chain rule. So how about 1 minus r to the third? That's as much as we can take without being too much. Then du is equal to negative 3r to the third. Whoops, not to the third, excuse me, squared. Du equals negative 3r squared. So I have a function and its derivative in the problem, a multiple of its derivative. The fact that this is 9 and this is negative 3, no problem. Negative 3 du is equal to 9r squared, and I need the dr. Just multiply both sides by negative 3. Now I have exactly what I need in the problem. The 9r squared dr, that right there, that becomes negative 3 du. And I have 1 over the square root of u, which is 1 minus r to the third. Now the question is, do I have something left that I can actually take the integral of? Yep, absolutely. With a little bit of work, we can get it. So we have negative 3 integral of u to the negative 1/2 du. Make it a power, so we can use the power rule. Add 1, negative 3, u to the 1/2, but I don't have a 2 sitting in front of there, so I don't have a 1/2 sitting in front of there, so I need a 2 to balance that out. So negative 6 u to the 1/2 plus c, but we didn't start with u's, we can't end with u's. I let u equal 1 minus r to the third. So negative 6 times the square root 1 minus r to the third plus c. A function and its derivative, that's what you're looking for. A function and its derivative. This next one, the 1 over x squared plus 16, we're going to use substitution, but it's a little different. We kind of break the rule that I just said. I said we need a function and its derivative. We don't get that in this one. We're going to let u something equal very not obvious. I don't know if that's good English, but you know what I mean. X over 4. We're going to let u equal x over 4, which is not clear. It's not apparent that that's what we should use. But I'm trying to get this to be 1 over x squared plus 1, or 1 over u squared plus 1. If I can get that, that's inverse tangent. So we do this. We say 4u equals x. We just multiply both sides by 4. Now we are going to use a substitution, but it's not the kind of the normal substitution that we see. If x is 4u squared, I do need the derivative, by the way, 4 du equals dx. I do need that piece. I don't want to leave that out. But now let's go back to what I was saying. If x is 4u, then this becomes 1 over 16u squared plus 16. But the dx becomes 4 du. Now that allows us to factor out a 16 in the denominator. Because I chose u to be this, and I can multiply, I get the 16u squared plus 16. So we have 4 over 16 integral of 1 over u squared plus 1 du. And that's what I was after. That was the goal of this problem right here. Get that to be u squared plus 1, because now 4/16, that's 1/4. Inverse tangent of u plus c. The derivative of inverse tangent is 1 over u squared plus 1. If I didn't start with u, I can't end with u. So we have inverse tangent of x over 4 plus c. And that is the antiderivative. Any questions on that? I want to do one more. It's almost the exact same, except we're going to let u equal x over 5. If it was 49, we'd have x over 7. If it was 81, we'd have x over 9. It's all the same stuff now. So that 5u equals x. 5 du equals dx. That's all we need. We got all the tools we need. We have 1 over 25u squared plus 25. That allows me to factor out that 25. That's the trick. And dx, this dx becomes 5 du. And I try to pull all constants out if we can get that accomplished. So we have 5 over 25. We factor out the 25 in the denominator, pull it out front, and we have what we need. We needed that u squared plus 1. So we have 1/5 inverse tangent of u, which happens to be x over 5. And then notice I'm writing every time plus c because it's an indefinite integral. Indefinite. Any questions on those two? It's all the same every single time. 26, we need a function and its derivative. We can let u equal x plus 2, du equals dx. But do we really need all that? Because the antiderivative of secant is tangent of x plus 2 plus c. Now, when the derivative of the inside is just 1, I don't really think I need to use substitution to do this, but you could. You could use substitution, no problem. But like I said, when the derivative of the inside is 1, I'm not really sure I need to use substitution. And as you play around with these, as you do these problems, as you practice it, I think you'll find out the same thing. All right, couple more, so hang in there. Function and its derivative. Function and its derivative. The derivative of cotangent is negative cosecant squared. So I almost have a function and its derivative. I can just let u equal cotangent of x, and du is equal to negative cosecant squared x dx. Don't take too much for the function. If I took the square root of cotangent of x, that's a much more complicated derivative, and I don't have enough to grab all of that. I gotta leave the square root. You can't grab too much so that your derivative is too complicated. I don't have a negative, so we just multiply both sides by -1. Now I have exactly this. I have cosecant squared x dx. I have that. I have the original function. We're ready to go. Integral of the square root of u, so cotangent becomes u, dx, cosecant x dx becomes negative du. You got to be careful with the multiples and careful with the negatives. Well, now the question is, do I have something left that I can take the antiderivative of? Did I grab enough? Sure did. Because this is negative integral of u to the 1/2 du. We add 1 to the power, which is u to the 3/2. We'll have to multiply that by 2/3, and that negative has to come along with it. So then we have plus c. So negative 2/3, and I think the u was cotangent. So cotangent of x to the 3/2 plus c. Questions on that one? You just have that negative there. Now if you take the derivative of this, it's going to be 3/2 cotangent to the 1/2 times negative cosecant, and that negative will make it positive, just like it is in the original. 34. All right, Matt. I need a function and its derivative. So what are you going to let u equal? I'm going to quiz you a little bit. This one's kind of tough. Tangent of x over 2. So we're going to let u equal tangent of x over 2. And I know you're sitting there going, what about the 7th? What about all that stuff? Well, remember the 7th power is really on the outside. So it's tangent of x over 2 to the 7th. That's on the outside. So here's what we can do. We have du is equal to secant squared of x over 2, but then times 1/2 dx. And we're like, well, we don't have the 1/2, but that's a multiple of the derivative. We're okay with multiples of derivatives, because now we can just multiply both sides by 2. So we have secant squared x over 2 dx. Now we're taking the integral of u to the 7th, because we have tangent to the 7th, and then secant squared x over 2 dx becomes 2 du, like that. Now the question is again, do I have something left that I can actually take the antiderivative of? Absolutely. We add 1. We have 1/8 u to the 8th plus c. Now 2 times 1/8, that's 1/4. Our u was tangent. So tangent x over 2 to the 8th plus c. And I'll bet if you look in the back of the book, it has this. Because we don't really put the 8 on the outside. That's how you write tangent to the 8th, right like that. That was tricky because that 7 kind of gets in the way. But the function is tangent, the derivative is secant squared. The last one. I show this one because you have to turn this into sine of x over cosine of x dx. Now, we have an issue, we have a problem here, because the derivative of sine is cosine, the derivative of cosine is negative sine, so we can really choose either one, because they are each other's derivative, but only one way works. The other one does not work. So, what do we pick as the u? You got a 50-50 chance. What do you think, CJ?
I think cosine.
Why cosine?
Taking the derivative to have sine, but where you took the derivative of sine of x, you get negative cosine.
So the negative's not the issue. You actually lucked out and got the right one, but I'm not sure you know why. Here's a why. Well, let's just do this. Let's do du equals negative sine of x dx. It's okay that we got the negative. That's not the issue. So you picked the right one. That's awesome. But let's say you wouldn't have picked the right one, which I really wanted you to do, by the way. So let's say u was cosine. No. The wrong one would be sine of x. And then you said du equals cosine of x dx. We really don't have a cosine in there. We have a 1 over cosine in there, not a cosine. Cosine doesn't exist in that problem. 1 over cosine exists in that problem, which is much different. So that's why you can't choose this one right here. You actually have to pick the denominator. Because then we can say, well, negative du equals sine of x dx, integral of negative du is the sine of x over dx. And we have 1 over u now. You can't do it the other way because you don't have a cosine. You kind of do, but it's really, like I said, it's 1 over cosine. So we have negative natural log of the absolute value of u plus c as the integral. And so negative natural log absolute value of u is cosine plus c. Now imagine, think about what we would get if we took the derivative of this. By the way, this is the answer. You don't have to continue on. But the derivative of that is negative 1 over cosine of x, but then times negative sine of x because of the chain rule. So negative times a negative becomes a positive. You get sine over cosine, and therefore that must be tangent. So you do get it, but you get tangent back when you take the derivative. Any questions on that? Now in the homework, I think you have to integrate something like tangent of x plus 2 dx. Well, the derivative of the inside is 1, so you don't have to worry about that part of it being substitution. You have to turn this into sine of x plus 2 over cosine of x plus 2 and let u equal cosine of x plus 2. U has to be the denominator, can't be the numerator. So there's a hint for your homework, because I had someone come up last period, actually first period, and go, what do I do with that? Well, what did I do in there? I turned tangent into sine over cosine.